Hello and welcome to another Common Core Geometry lesson by eMathInstruction. My name is Kirk Weiler and today we're going to be doing Unit 3, Lesson Number 1 on drawing inferences from givens. Wow, that sounds exciting. But let me frame this for you a little bit better than just the title of the lesson. You see, we're moving now into Unit 3. Unit 1 just sort of laid out geometric terminology, some measurement tools, things like that. Unit 2 was all about transformations, rigid body motions, the idea of congruence, and using transformations to prove congruence, or at least to investigate it. Unit 3 is going to be all about using logic, givens, and what's called Euclidean proof in order to investigate different types of geometric figures, mostly triangles. All right? And a first step in doing that is understanding how to take things that we're given, and givens are things that we're told to be true, and then making inferences or taking things from those givens based on what we know. All right? And let's kind of get into it because really, as the slide says, it began with Euclid. Okay? There was this guy named Euclid. All right? Right, there was no photographs when he was alive because he lived 350 to 300 years BCE. All right, we are talking 2,300 years ago. Euclid really was the father of basically all geometry. And he wrote a book, all right, called The Elements, Euclid's Elements. It was actually a series of books. And again, these things are remarkably old. But the weird thing about them is that the geometry that was done in Euclid's Elements, you're doing a ton of it this year. 2,300 years old. And the geometry that Euclid developed is essentially what you're going to be starting right now. Because what Euclid believed was that if you started with some basic assumptions, some basic axioms or postulates, and we looked at a few of those back in Unit 1, then you could build an entire what's called axiomatic system from it and prove all sorts of important geometric results. He also liked constructions quite a bit, and we'll get into those in the next unit. But let's dive right into what it means to draw inferences from givens in a problem. All right? And let's do it right in exercise number 1. Exercise 1. In the following diagram, it's given that C is the midpoint of AB. In other words, here's a given. Whenever we have a given like this, what we do is we say, all right, that's what we know. That's what the problem has told us. That's what we're going in with. Okay? What conclusion can you draw from this given? What conclusion can you draw from this given, and why? I bet you can even come up with the conclusion that you can draw from this given. So, take a moment, pause the video, and write something down. Let's do it. So, what can we really say from this given? If I'm told that C is the midpoint of AB, then what I should be able to say is either AC is equal to BC, or pretty much equivalently, segment AC is congruent to segment BC. Now, why, right? The why is the reason, and the reason really is just basically what a midpoint is. The reason is because a midpoint divides a segment into two congruent segments. It's that simple. A midpoint divides a segment into two congruent segments. That's what's known as a reason. This is a given, this is a statement, and this is the reason for that statement. All right? Now, being able to draw proper inferences from any givens is all about knowing your geometric terminology. So we're going to review a little bit of that right now, and then we're going to go on and continue to draw inferences from givens. Let's do that. All right. Terminology is extremely important in geometry. You must know what you know and know what you don't know based on the givens of the problem. And by the way, knowing what you don't know is almost as important as knowing what you do know. You do not want to draw conclusions if you can't do so based on the givens or based on something else that's inherent in the geometric problem. So let's review a little bit of the terminology. Geometry terms. First, segment bisector. A line, ray, or segment that passes through the midpoint of another segment. Let me just bring up the screen a little bit here so you can see it. So in this diagram, line S is the segment bisector of segment AB, right? Because it passes through the midpoint. Just like segment bisectors, we can have angle bisectors. A line, a segment, or ray that divides an angle into two congruent angles, two angles with the same measure. And again, in the diagram here, what we see is that we see ray BD, right, is the angle bisector of angle ABC. And finally, at least for now, perpendicular, any two lines, segments, or rays that intersect to form strictly 90 degrees or right angles. For example, right, AB is perpendicular to CD if the two lines AB and CD form right angles. So for instance, let me slap some points on here. Let's say that's AB. Let's say this is CD, right? Then these two lines are perpendicular to one another. One thing that's important, going back to that idea of know what you know and know what you don't know, perpendicularity is all about angles. It has nothing to do with lengths. So if we know that two things are perpendicular, don't assume that one of the segments is bisecting the other segment. Perpendicular just means the formation of right angles, 90-degree angles. Let's use a little bit of these terminologies. Can't say that. Let's use a bit of this terminology now to draw some conclusions or inferences from givens. All right. Take a look at exercise number 2. In the diagram below, it's given MBN, and AB is perpendicular to MN. And again, very, very important that when you see that kind of symbolism, that you know that that means perpendicular. Your teacher certainly is going to assume that you know it, and if all you do is look at that and try to go, well, I don't remember what that upside down T means, maybe it means bisect or something, then you run into a problem. Anyway, let's take a look at what letter A is asking us to do. What does the first given, i.e. this thing, tell you? What does that given tell you? We've talked about this before. Take a little bit of time and think about what that given tells you. All right, let's talk about it. When we see three letters with a segment bar over it, or a line bar or a ray bar, either way, it tells us that M, B, and N are collinear. Doesn't really quite look like an O. There we go. Are collinear. Also from that means that the measure of angle MBN must be a straight angle or 180 degrees. Now, this is oftentimes a given that in a problem you kind of look at and you might even overlook it. You might look at it and say, I don't know, it doesn't even seem like it's telling me anything. But it truly is, because again, the idea is even though MBN looks like it's a straight line segment all by itself, you know, there could be kind of a little bit of a bend at B, maybe some angle other than 180. This tells us all 3 points lie in a straight line. Let's take a look at letter B. What conclusions can we draw from this given? From this given. All right, write down what conclusion you can draw from that given. Pretty simple, right? AB is perpendicular to MN. Don't be afraid to draw on diagrams in this course. Very, very important, right? What we can say from that is that angle ABN and angle M, well, we'll stick with the A going first. Angle ABM are right angles or equivalently, they measure 90 degrees. Okay? So that's simple enough, right? We're told AB is perpendicular to MN, ABN and ABM are right angles, or they both measure 90 degrees. Another thing you can then get from that, so it's not your first conclusion, but you can get this from it, is that these two angles have to be congruent, right? They're the same size, and that's what it means for two angles to be congruent, is that they have the same measure. Let's take a look at the last part of this problem, which is quite important. Letter C asks, can we conclude that MB is equal to NB? Can we make this conclusion? Think about that for a minute. And the answer is no. No. Now why? Why can't we say that? Well, we can't say that these two segments have the same length because we don't know or better yet, we weren't told, but I'm going to keep it with this. We don't know if AB bisects MN. We only know that it's perpendicular to it. You could also say we don't know whether B is the midpoint of MN. Now be careful. What I don't want you to say is, well, I took my ruler out and I measured MB and I measured BN and they're the same length, so I know it. The point here isn't to talk about what we could find out with measuring tools. It's what we can conclude based on what we are told in the problem. This unit's not going to have a lot of measurement in it. Let me be very clear about that. This unit is really all about being told certain things in a problem and then seeing what kind of conclusions we can make based on what we're told. Let's keep going. All right, some additional terminology. Now, the last few pieces of terminology you should have known pretty well because we've talked about them throughout the course so far. Some of these pieces of terminology are going to be a little bit new to this course, although you've likely seen them in 8th grade. Perpendicular bisector. Well, that's one we've already seen. A line, ray, or segment that passes through the midpoint of another segment and makes only right angles with it. So in this particular diagram, whoops, I turned one on I didn't want to right away. In this particular diagram, CD is the perpendicular bisector of AB. It's both perpendicular to it and it's slicing it in half. Now let's talk about the second diagram. The median of a triangle. A line segment drawn from the vertex of a triangle to the midpoint of the other side. The median of a triangle. A line segment drawn from the vertex of one of the three vertices of the triangle to the midpoint of the other side. Every triangle has three medians. All of them do. Let's take a look at the final piece of terminology for today. The altitude of a triangle. A line segment drawn from the vertex of a triangle such that it is perpendicular to the opposite side. Sometimes this will be called the height of the triangle, right? Whenever you're doing that classic area of a triangle equals 1/2 base times height, the base is oftentimes a side length of the triangle, but the height is the length of an altitude to that base. Now, don't get me wrong, an altitude can be a side of the triangle, but only if that side is perpendicular to the side it's being drawn to. Hopefully that made sense. So in here, again, AD is not a side of the triangle, but it's an altitude because it's perpendicular to side length BC. Okay, now using these pieces of terminology, let's draw some inferences. Exercise number 3. In the following diagram, triangle ABC is drawn such that point D lies on side BC and point E lies on side AC. Read the givens below and then state all conclusions you can draw from these givens. Explain your conclusions. All right, so here are the givens. This is what we are told about this diagram. BE bisects angle ABC, and AD is a median drawn to BC. All right, I'd like you to take a few moments and write down everything that you can figure out just based on this information. Go ahead. All right, let's go through it. So there's a couple givens here. The first one is the fact that BE bisects angle ABC. All right, here's BE, and here's angle ABC. There's a lot of messiness up there right now, so I'm just going to erase it. But what do I know? Well, I know that an angle bisector divides or cuts an angle into two congruent angles. So what I can say based on that given is that angle EBC, which is this one right here, right, is congruent to angle ABE, which is right here. All right? Or you could say equivalently, the measure of angle EBC is equal to the measure of angle ABE. Now, part of this, though, isn't just making the conclusion, but it's also explaining why we know that conclusion is true. So just to free up a little room, I'm gonna get rid of this piece, and I'm gonna explain this. Well, why do we know this? That's because angle bisectors, let me put it, an angle bisector, oh boy, my spelling, divides an angle into two congruent angles. Right? Took me a little bit to get that written out, but an angle bisector divides an angle into two congruent angles. So that's this one. Now, how about the fact that the AD is the median, is a median drawn to side BC? Well, what can we say there? We can say BD is congruent to CD. BD is congruent to CD. This length is congruent to that length. And again, why is that? Well, that's because a median is drawn to the midpoint of the opposite side. All right, a median is drawn to the midpoint of the opposite side. Of course, midpoints divide a segment into two congruent segments. All right, so some conclusions we can make based on those two givens. All right, let me kind of step out of the way a little bit. Take a moment if you need to write any of this down, and then we'll move on to our last slide. Okay, let's do it. One more. Exercise number 4. In the diagram shown below, triangle MNS and triangle TWS are drawn. Good to know. We know the following givens. Given NW is the perpendicular bisector of TN. That's it. MW is the perpendicular bisector of TN, and letter A says, state all conclusions you can make from this one given. Explain your conclusions based on the definition of a perpendicular bisector. All right. Talk to me about all the conclusions you can make based just on this. Take a few moments. All right, let's go through it. Remember, MW is the perpendicular bisector of Tn? Well, one thing I can say right away is that side or segment TS is congruent to segment NS. By the way, of course, if you have the letters reversed on those segment notation, that's completely okay, right? And why? Because a bisector divides a segment into two congruent segments. Now, that's one conclusion we can make, but that's only the bisecting part of perpendicular bisector. The other part is the perpendicular part, right? And of course, from the perpendicular part, we would know that this and this are 90-degree angles. So I can say angle TSW and angle MSN are right angles. And again, the reason being is that perpendicular lines or you could say segments, perpendicular lines form right angles. Perpendicular lines form right angles. All right? You get a lot of information when you're told that something is the perpendicular bisector of something else. So watch for that given. It's a pretty powerful one. Let's look at the last part of this problem. In letter B, it says, is TS an altitude of triangle TSW? Why or why not? So is TS, segment TS, an altitude of triangle TSW? Think about this for a moment. Yes, no, and why? Well, I'm hoping that you said yes. Why? Because it is a line segment. Let me put a little line there. Drawn from the vertex of triangle TSW perpendicular to the opposite side. All right? So altitudes are important most of the time in your garden variety of triangle, right? When we draw an altitude in, it isn't one of the sides of the triangle. In fact, it doesn't even have to be inside the triangle. You could have something like this, like a nice obtuse triangle, and then dashed line. That would be an altitude right there. But if you have a right triangle, let me get some space here like we did right there, then one of the side lengths, this one, and actually this one, are both altitudes because they're both drawn perpendicular to opposite sides. All right, it's just what an altitude is. Make sure that you spend some time memorizing this terminology. It's going to become increasingly important in the proofs that we do in this unit. All right, let me step out of the way for a second, take a look at anything that you need to, copy it down, and then we'll move on. All right, let's do it. In the lesson today, what we were trying to do is refresh some geometric terminology that we've seen before, introduce some new stuff that you haven't seen at least yet in this course, and finally also understand how we can take things that we're told to be true, known as givens, and then reach conclusions based on those givens. Very, very simple ones. These are almost like what would be called like 1 or 2 step proofs. Very, very simple stuff. Now going forward, what we're going to be wanting to do is take givens and string together a bunch of sets of logic in order to reach much greater conclusions than just these simple one-step wonders, if you will. All right, for now though, I'd like to thank you for joining me for another Common Core geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.